Good evening, class. Uh, in today's class, we will be covering the topic related to tight binding model, focusing primarily on the graphene, 1D lattices. So, having said that, just let me give you a quick recap. That in last class we discussed the structure of the graphene, where it is made up of two triangular lattice interpenetrating, and that results into the linear dispersion, which you see here. And these points are known as the Dirac point or K points. At these points, the energy of the basically the graphene system is effectively zero. We call it at a zero energy point. Above this is the conduction band, and below it is the valence band. Yeah. So now in this problem, in this class, the first problem which I will phrase will be determining the position of these K points given the energy equations relation basically. So let me put forth the question. So the question goes as the energy Hamiltonian is given. This is question number 1. Given the Hamiltonian H, which goes like H equals to 0, 0, there's a term Fk, and then there's a term F conjugate K. So it's F star K is complex conjugate of Fk, and where the Fk is minus t, t is the hopping parameter, e to the power I kxa plus 2 exponential minus I kxa by 2, and cos ky cos square root 3 by 2 kya. And the question says that in order to find the position of Dirac points, take Fk is equals to 0, or the complex conjugate F star k is equals to 0, and then determine the position of k and k prime. Okay, so when you have your graphene structure, which is honeycomb, like this, right? At every corner, you have these points, these Dirac points. So this is 1 point, one will be here, and one will be here. These three are of one kind. Let's call the green one as the K. This is K point. This is also equivalently K point. Then similarly, there will be K prime. Let me put it in some maybe different color. Red color. These 3 points are quantum mechanically different, and this is something which we call isospin in the case of the graphene. So along with the spin degeneracy, these are the isospin degeneracy, K and K prime. So they gives the two inequivalent point. And in this question, we are asked to find the values of the K and the K prime coordinates given the value of the Fk. So starting at the K point, as the question says, we'll have to take Fk equals to 0. So if you look at the expression of the Fk, it is e to the power I kxa plus 2 e to the power minus I kxa by 2 cosine of under root 3 by 2 kya is equals to 0. And if you just play with the equations, what we will get is 2 cosine square root 3 by 2 kya is equals to minus of exponential 3 by 2 I kxa. Similarly, Fk prime, the complex conjugate will also be 0. And if you take the complex conjugate Fk star, it will be e to the power minus I kxa. So wherever the iota is there, just replace it with the minus iota. 2 e to the power iota kxa by 2 cosine root 3 by 2 kya is equals to 0. This gives us 2 cosine under root 3 by 2 kya is equals to minus e to the power minus 3 by 2 iota kxa. Let's label the equation. This maybe this is equation 1 and this is equation 2. And since the RHS part of the equation 1, if we compare equation 1 and equation 2, the LHS part is the same, RHS part is different. So they equate. So comparing equation 1 and 2 gives you e to the power 3 by 2 I kxa is equals to e to the power minus 3 by 2 I kxa. So if you take it on the other side, it will be e to the power 3 by 2 iota kxa minus e to the power minus 3 by 2 iota kxa is equals to 0. And we know that e to the power iota x is cosine x plus iota sine x. So e to the power x minus e to the power minus x will be nothing but 2 iota times sine 3 by 2 iota kxa is equals to 0. This iota will not be there. Kxa will be equal to 0. And if we solve this one, sine 3 by 2 kxa is equals to 0. Sine kx equals to 0 means kx is equals to m pi, right, where m is an integer. So similarly here also 3 by 2 kx a is equals to n pi, where n belongs to integer. So this is the equation number 1 or equation number 3. So this was the one case. Now the second one which we have is we can divide 1 and 2. So divide equation 1 by equation 2. If you do so, what we get is e to the power iota 3 kxa is equals to 1, and we can divide again. We can divide the equation by e to the power. You can write it like 3 kxa by 2 is equals to e to the power minus iota 3 kxa by 2. So this is effectively the same thing, and in that case this is 2 and pi by, yeah, there's no need of dividing equation 1 and 2. I think they will essentially give you the same result basically, at least in the form of the kx. They will give the same result, so no need to divide it. Here only we can get the relation. So if you look at the equation 3, we get the kx is equals to 2n pi by 3a. So this is our equation number 4. So this is about the kx. Now since we have the kx, and in equation 1 and equation 2, either of them we can use to determine the ky. And if you know the kx and ky, we know the position of the Dirac point, because the position of Dirac point is nothing but kx and ky. So substituting equation 4 in equation 1. So if we substitute it, what we get is 2 cosine under root 3 by 2 kya, which is the LHS part, is equals to minus of e to the power 3 by 2 iota kxa. Now in place of kxa, we substitute the value, and minus e 3 by 2 iota kx is 2n pi by 3a times a. So this is like 2 cosine root 3 by 2 kya is equals to 3 cancel, 2 cancel, a cancel, and what remains is e to the power iota n pi. Right now, since this is there, so we can write it like 2 cosine under root 3 by 2 kya is equals to minus cosine n pi plus iota sine n pi. For if n is an integer, sine n pi is always 0, so this term always goes to 0. Now the only thing remains is cos n pi. If n is 1 or m plus, basically 2m plus 1, if it is an odd integer n, then the cos n pi will be minus 1. If n is an even integer, then cos n pi will be plus 1, and on basis of that only we'll get the number. Yeah. So for n equals to 2m plus 1, cos n pi is minus 1, where n is equals to 2m, cos n pi is 1, where m belongs to integer. So what effectively we get is 2 cosine root 3 by 2 k by a is equals to plus minus 1. We can take inverse of it also, so we just do it cos root 3 by 2 k by a is equals to plus minus half, and we know that uh, cosine this plus minus half is essentially 2 pi by 3. So this is cosine 2 pi by 3 this is pi minus pi by 3 for the negative sign. So if you just compare it, what we get is ky is equals to 4 pi by 3 root 3a, and this is if your yeah, so if your kx is, it depends on the value of the kx. Your kx is 2 n pi by 3a, right? Your kx is 2 n pi by 3a. If you take n is equals to 0, then in that case only the for n equals to 0. So this means even number, so that only the negative, and what you get is this one, and kx is equals to 0. So what your coordinates are 0, 4 pi by 3 root 3a. This is for k. Now this is the k, coordinates of the k, right? For this one, that's it. For k prime, the y needs to be flipped, right? So for k prime, the coordinates will be 0 minus 4 pi by 3 root 3a. This is for k prime. And if you have any question or doubt on this one, you can raise your hand or ask in the comment section. I'll be happy to address your concern on this one, because this is like an important topic. Yeah. In the sense that just by giving the form of the Hamiltonian, you determine these points which are known as the Dirac points, their positions. So these two we have determined. If you take it as like this direction as the y, and this is as the x, and then this is as z, then we have determined the position of these 2 points. These 4 points also you can determine if you take. So here we did n is equals to 0, but if you do n is equals to 1 or n is equals to 2 minus 1, then you can get the position of these points also. There should be one more value corresponding to plus half value. uh, I think you are talking about here the okay, see, there won't be, because I'm taking n is equals to 0. For n is equals to 0, for n equals to 0, this case gets eliminated, only this one survives, right? Because if n is equals to 0, your m has to be, your n comes into the even category, not in the odd category, right? because if m equals to 0, then only n becomes 0. If m equals to 0 here, in this case, then n cannot be 0, right? So only this case survives, and for that reason only, till this point I considered both of them. But now if I go for n is equals to 0, a one special case, that I am taking only n is equals to 0 case, then in that case only this condition satisfies, this is not satisfied, and then only I'm taking this to be minus half, and the minus half corresponds to the second quadrant. This quadrant, this is first, this is second, this is third, and this is fourth. So the second quadrant, pi minus pi by 3, this will give me negative of the cos 2 pi by 3 basically. And is that clear your doubt, Mansi? Like, because I could see in the chat that you asked this question, that there should be one more value corresponding to plus half value. Yeah, oh, good. Yeah, if this is clear, then we'll move on to the next question. That for the this is also in case of the graphene only. So the question is question number 2. That for graphene the energy spectrum is graphene the energy spectrum is given as E, total energy E, is equals to E naught, that's the baseline energy, plus minus T. T is the Hoping parameter, that the nearest neighbor Hoping parameter basically, and 1 plus 4 cosine ky square root 3 by 2 times A naught cosine kx 3 by 2 A naught, plus everything is under square root only, so I'll put this curly bracket, 4 cosine square ky square root 3 by 2 times A naught. Yeah. For and now the condition is given that E naught is equals to 0 and T is equals to, let's say, 4 EV. Let's say I'm just taking it to be 4 EV, right? And or minus 4 EV. Then in that case, determine the energy at Dirac point. And Dirac point we estimated, right? 0 and 4 pi 3 root 3a. Can anyone tell me what will be the answer for this one? Because this one we have discussed while estimating the first question, that how we extract the Dirac points, basically the coordinates, and it's just reverse of it. So in this case, we are asked to determine the energy given the Dirac point. In the earlier one, we determined the Dirac point given the energy equation. Yeah. Okay. So let me just put the answer. Since at the Dirac point, as I said, that the energy is 0. This is 0 energy point. Zero energy is just, we shift it, we call it to be the zero energy. We take the E naught to be 0. Actually, this energy is actually epsilon naught. This epsilon naught which is there. This is epsilon naught, and we always take, because since uh, if it is a scalar quantity and we can move the reference scale, because energy whatever we measure is relative, right? Relative to something, and we take this E naught to be 0 for simplicity, and that's what we have done in this equation also. We take E naught to be 0. So if we do so, let's just replace the kx and the ky in the equation and we will get the answer. So E is equals to, this is solution now, E is equals to E naught is 0 plus minus 4 under root of 1 plus 4 cosine ky is 4 pi by 3 root 3a cosine kx is 0 plus 4 cosine square ky is 4 pi by 3 root 3 times root 3 by 2. So if we solve this one, what we get is 4 plus minus square root of 1 plus 4 cosine cos 0 is 1 and root 3 cancels. This is 2 pi by 3 plus 4 cosine square 2 pi by 3. And this is plus minus 4 square root of 2 pi by 3 is nothing but a minus half, and this is 4 into 1 by 2 square. So E is equal to plus minus 4 square root of 1 minus 2 plus 1. So these three cancel each other, and what we get is the answer to be the 0. So the energy at the Dirac points at this level is E naught is equals to 0. So this is how we determine the energy given the, if the energy expression is given, we substitute the value of the kx and the ky at the Dirac point and we get the energy equation, energy at that point, particular point. So given the different kx and the ky's in the Dirac point, we can estimate the energies. For example, both kx and ky both are 0. In that case, the energy will be 1 plus 4 plus 4. 4, 4, 8 and 9. So it will be 12t, because this 1 will be there. 1 plus 4, 9 square root of 9 will be 3, and 3 times t, where t is 4. So that will be 12. So that's in between here. So if you have this zone here, if your kx and ky, at these points the energy will be high. Your energies will be very high. And this is uh, what is there in the case of the graphene. If you look at the 3D dispersion of the graphene, you will see at this point the energy is the maximum energy levels, and at this point they come down. So what happens is, like, these go like this one also comes like this one also comes like this is 3D contour kind of thing. This also comes like this also comes like this. So at this point the energy is the maximum, and at this point the energy is the 0. The absolute energy is minimum at these points, Dirac points, and it is maximum at this point. This point is known as the gamma point. This is K, and this point is known as M points. So in case of the graphene, let me just mark the points, how we call the points in the brilliant zone. So the point which is at the center is known as the gamma point. These corners are known as the K and K prime. In between point is known as M point. So whenever you do the calculation, you span these area theoretically. Gamma Km and gamma M K prime. Or generally what you do is gamma K M K prime and then again gamma. So that gives you it like line cuts of the energy equations dispersion. Is this question clear? The second question, because if this is clear, then we'll move on to the next question. Or if you have any doubt on this one, you can ask in the chat section. Yeah, looks like there is this is clear. So then I'll move on to the next question. So the next question is again inspired from the class notes. This is question number 3. Since this is the problem which we have discussed by this has been discussed by Professor Agyat Rapta in the course, and this is like a two-dimensional unit square lattice where you have the tight binding Hamiltonian, and then we'll determine its minimum or the maximum energy. So the question goes like, for a two-dimensional unit square lattice, what value of E corresponds to half filled band given E naught is equals to 4 and T hopping parameter is equals to 1. Hmm. Yeah. So the question which is being asked in this problem is, you have your band structure in which you have your minimum energy and maximum energy E max and E min, and it is asking at what value of energy this will be filled. Right, this will be half filled, so the energy states will be half filled. So to that energy which we E half filled will be nothing but E minimum plus E maximum divided by 2, right? That will be the E half. Now to determine, so first we'll have to see the energy expression for a two-dimensional unit square lattice. We know that energy goes as E naught, that's the shift in the energy, and then 2 times T hopping parameter, and goes cosine kxa plus cosine kya. Yeah. Now if we substitute E naught and value of T, what we get is 4 plus minus 2 cosine kxa plus cosine kya. For minimum, for E minimum, kxa is equals to kya is equals to 2m plus 1 pi, right, where m belongs to integer, and E minimum will be nothing but 4 plus minus 2, 4 minus 2 basically, here should be plus 4 plus 2 times minus 2, that will be 0, and for E max kxa is equals to kya is equals to 2m pi, where m belongs to integer, and E max will be nothing but 4 plus 2 times 2, that will be 8. Now if you want to know the energy at which these levels will be half filled, it will be nothing but E minimum plus E maximum divided by 2. So E half will be 0 plus 8 divided by 2, that will be 4. So this value will be 4. E max is 8, E min is 0. Is there any doubt or question on this one? Okay. Generally, the values are in the electron volt, but since in the question, the value of the hopping parameter T, the units are not given, then I won't say it's in the electron volt. But yeah, if I modify the question T to be electron volt and E also to be the electron volt, E naught also to be the 4 electron volt and T equals to 1 electron volt, then yes, this value will be also electron volt. Yeah, now the values are in the electron volt. So we should go with the dimensions. Yeah, right. So we should always uh, keep in mind of the dimensions, because without dimensions the quantity uh, can mislead to the wrong answer. Yeah. So now let's move on to the next question, which is again from the same similar tight binding model, but with a special case that when you are near, let's say, the Dirac point or the low energy regime, where your carrier concentration is very low, where your carrier density is very low. In that case, how your dispersion will look like? Will it be isotropic, anisotropic? What kind of nature it will be having? On all those things. So this question is framed on that. So the question number 4. So the question is, for a square lattice at very low carrier densities, what is the shape of the Fermi surface? The shape of Fermi surface. So again, will it be a square? Will it be a distorted square? Will it be a circle, ellipse, or distorted circle, or a rectangle? This we'll have to figure out. So the energy expression which we have from the tight binding now, we know that for two-dimensional square lattice it goes as E naught plus 2 minus 2t cosine kxa plus cosine kya. Since in the question itself, it's for, let's just revise the relation between n and k. K is proportional to under root n, right? That's how it goes in the 2D, in two dimension. Okay. So for low carrier concentration, K is also very less than 1 by A. And if that's the case, then kxa and kya will be less than 1. And now we can expand the cos kx, right? So we know that cos x goes as 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial plus minus x to the power 6 by 6 factorial, and so on. It keeps going, the series, right? And for if our if our kxa and kya are less than 1, then we can neglect these higher order terms, right? And we can only keep this 1 minus x square by 2 factorial. So cos kxa will be nothing but 1 minus kxa square by 2, and cos kya will be 1 minus kya square by 2. One second, I'll just take a break. Yeah, so we can neglect the higher order terms and can keep only the first order parts and replace it in equation number 1. Replace 2 in 1. So what we get is E is equals to E naught minus 2t 1 minus kxa square by 2 plus 1 minus kya square by 2 is equals to E naught minus 2t. This is 2 minus kxa square by 2 plus ky a square by 2. So this is like E minus E naught by t is equals to, this goes as minus 4 plus kxa square plus ky square. So this is essentially kxa square plus kya square is equals to E minus E naught by t plus 4, and what we get is kx square plus ky square is equals to E minus E naught by t plus 4 by a square. Let's call this quantity as maybe c. So this is the equation which we have is kx square plus ky square is equals to c square, and this is an equation of circle, we know. So in the 2D, two-dimensional lattice, square lattice, which is like this, right? And the hopping parameter to be t, its dispersion relation for low carrier density will be isotropic in nature. That will be circular in nature, and the radii being c and the kx and the ky. This is kx This is ky. Yeah. Is there any doubt or question on this one? Because see, generally when we see in the Fourier space for square lattice, the Brillouin zone is square. But here we look at the energy dispersion relation, that how the energy is scaling, right, as a function of kx and ky. And we see that the surface which it contours is a circle, and not a square. So, see, saying such last slide, please. I don't get your point. Which one is the last slide? So this is page number 116. The current which I'm there on. Okay, 117. 117 is this one. Yeah. The calculation part you can check. Sometime I might miss some negative or positive signs, so that you can see. But the result remains the same. That it's a circle. That's a standard result. Any question or doubt? If you guys have, you can ask in the comment section. If not, we'll move on to the next question. Okay. If there's no such question, then I will move on to an interesting result, which is based on again graphene. Generally, what we have studied in our condensed matter is this is question that if you look at the density of states, right, in 1D, 2D, and 3D. So in 1D, I think they go as e to the power half. In 2D, they are 0, and in 3D, they go as e to the power minus half. Right? And that's what the trend is. And so if I draw it, density of states versus energy. So this is e to the power half. And for 2D, it's constant. And for 3D, and that's what we have learned so far in our basic condensed matter. And this comes from the fact that we assume our dispersion relation to be of the parabolic, right? That the energy goes as k square, but that's not the case in case of the graphene. In case of the graphene, energy goes as linearly with k, not k square. I think here I misinterpreted this one. This is should be the 3D. 3D goes as e to the power half, and 1D goes as e to the power minus half. As far as, yeah, I think, yeah, this is the correct one. You guys can check it also, but I think that's the one. In 1D, it goes as e to the power minus half. Density state is very high at low energies, and in 3D, it's just opposite. Yeah, that's what I think. Yeah. Yeah. So the primary essence is that in 2D, DOS is almost constant, but that breaks down in case of the graphene, and we will see that. So the energy expression which we have in the case of the graphene. So the question is, determine the density of state. So first we'll have to find a relation between uh, carrier density and the wave vector k, and then we'll move on to find the relation between the density of state. Okay, so in two dimension, again same theory which we have done, the total number of states will be equals to integral over the real space. This is the real space and this is k space. So d2k d2 basically this is dx dy. So this will I'll call d2l by 2 pi square, and this will be the real part I will take out. So d2l will be nothing but the total area. Total area I will divide it, and this is k d2k by 2 pi square, and by a is nothing but carrier density, and there will be a 4 factor of 4 also, which is you can divide it as 4 is equals to 2 times 2. 2 is because of the spin of the electron, and 2 because of the value which we discussed in this class, k and k prime. They are inequivalent points, so they will also come here. So n is equals to 1 by pi square, and d2k will be nothing but pi k square. So your k is nothing but k square. K is equal to under root n pi. So this is one relation which we have. The another relation which we have is energy. So E is equals to h bar k Pf. So taking square of equation 2, E square is equals to h bar square k square Vf square, right? And substitute 1 in 3. So if we do so, we get E square equals to h bar square k square is nothing but n pi Vf square. Density of state is nothing but del E by del N. Right? So we'll take the derivative of equation 4. Taking derivative of equation 4 with equation with respect to n. So this will be 2e del E by del N equals to h bar square, n is n pi Vf square. One second, I'll just check one thing. I think I'm this is density of state, right? I think I quoted it wrong slightly. It should be del n by del E and not del E by del N, as far as I now remember. Let me just see it once. I think, yeah, it's inverse. Actually, del N by del E is the density of state. So density of state is equals to del N by del E is equals to 2E by h bar square pi Vf square. So this is constant, h bar is constant, that is 1.05 into 10 power minus 34 joule per second. Pi we know is constant, 22 by 7. Vf for graphene is also constant, which is equals to 3 hopping parameter times interatomic distance by 2, which turns out to be, I think, 1 into 10 power 6 meter per second. And so del N by del E is proportional to energy. Graphene is also a 2D material, but here density state is proportional to energy, whereas in classic part density state is constant, because here your energy expression is h bar square k square by 2n parabolic, and here in the other one your energy expression is linear, plus minus h bar kvf, like this. And that's because of this linearity, now your density state goes as proportional to energy and not a constant. Is there any doubt or question on this problem? Like like in the two being the 2D also, the graphene density state increases linearly with the energy. So if I draw the density state, it will be density state energy, it will go like this on both sides, negative and positive side. This density state will increase, whereas for the system like the two-dimensional electron gas, which is not like graphene and have parabolic dispersion, their density state will be constant. Any doubt or question on this one? If not, then we will end the class like with this note. And uh, if you have any question or doubt, please ask in the comment section. Okay, if there is no question, then bye bye class. Happy Holi to all of you. Enjoy, and we'll see you guys on the Saturday, coming Saturday, with the next session. And till the time, enjoy. Happy Holi.